All right, EEE203 midterm practice problem number 4. This is a convolution problem. The impulse response of an LTI system is given by h of t equals e to the negative 2t times the unit step, and that's plotted over here in orange. So this is orange. That's plotted over here on the left in orange right here. And then what is the output y of t when the input x of t equals the unit step evaluated at 0 minus a unit step delayed by 2. Or I shouldn't say the unit step evaluated at 0, just a standard unit step minus a delayed unit step. And that's over here in blue. All the unit step is it turns it on at t equals 0, and this is going to turn x off at t equals 0, or excuse me, t equals 2. And that's what this is doing. That's what x of t is doing. That's why we have this. So I have this pulse function right here. All right. So, and the convolution integral. Let's remember what that is. So y of t is equal to x of t convolved with h of t, and that is equal to the integral over all time x of tau h t minus tau d tau. Now if you come over here on the left, I've plotted, well, here's right here is, this is a plot of x of tau and h of minus tau. And you can see that h of minus tau is just h of t up here, and it's just flipped. And if you look down here, here's a couple more plots just to show h, or just to show what happens as the input x is being passed through the system. So this is at t equals -1. This is at t equals 0. This is at t equals 1. This is at t equals 2. This is at t equals 3. And this right here is at t equals 4. And this makes sense because if we were to pass this pulse through the system, right? Well, this right side of the pulse right here, this is going to enter. This is going to enter, or excuse me, the left side of the pulse, let's get that off. The left side of the pulse, which is right here, is going to enter this system first. So this side is going to be passed into the going this way. And I understand we flipped h of t, but I just did that to keep in accordance with what the convolution integral looks like. But remember that this is also equal to h of t convolved with x of t. And these are just dummy variables, so we could switch these. We could switch the order of these if we wanted, and we could have h of tau times x of t minus tau. But we'll keep it going as we do. Now for t is less than 0, if we look here at the top, well, we have no interaction. We have h being multiplied by 0 right here. So that's 0, and then we have 0 being multiplied by 0, so here's 0 times 0, and this little snippet screen, this snapshot here, or all of right here, we have 1 being multiplied by 0. So the convolution of y of t, x of t, involved with h of t, is going to be equal to 0 for t less than 0. And that takes care of one part. So now what we're left with? We're left with finding out what happens after t equals 0. And that's going to be equal to the integral from 0 to infinity, x of tau times h of tau minus, or h of t minus tau d tau. And let's come back over here to our graphs on the left. Well, we have two different interactions. We have two different integrals that we now need to break this into. So right here in t equals 0, in this middle, or the second plot down, our system and our signal are just beginning to interact right here, right? And then at some later time t, we could say, well, at t equals 1, we have an interaction from 0 to t equals 1, right here. Here's our interaction of our system from here to here. And then at some later time, we have an interaction from 0 to t equals 2. So for these three right here, we're going to integrate along the length of the box that interacts. And that's going to depend on what time we take that snapshot at. So that's going to go from 0 to t if t is less than 2. And then right here, or I guess it kind of overlaps with these ones. Let's go with a different color pen. From these ones here, if we take a look, well, we're still integrating from 0 to 2, or now we're integrating from 0 to 2 because that's what's interacting. We have our pulse interacting with the tail of this decaying exponential, which is non-zero. It only becomes 0 at infinity, which that's arbitrary, or trivial rather. So we still have to account for this interaction right here. So we're going to integrate from 0 to 2 if t is greater than 2. And well, actually greater than or equal to 2. Let's remember the unit step is equal to 0 for t less than 0 and 1 for t is greater than 0. So it's not really defined at t equals 0, but don't get hung up on that. So we can now do our integrals. So for and we can actually do it kind of generic to start. Let's just go from a to b. So y of t. Let's do the integral from a to b of x of tau h of t minus tau d tau, and x of t is just a pulse with magnitude 1, so that's going to be 1. So we'll swap out our h, and that's from a to b of e to the negative 2 t minus tau d tau, and we'll do a little bit of manipulation here, and we get e to the negative 2t plus 2 tau d tau, which is equal to e to the negative 2t times e to the 2 tau d tau. And we're integrating with respect to tau, so we treat t treated as a constant, and we can pull that out front, so we get e to the negative 2t from a to b, e to the 2 tau d tau, and that's pretty simple integral. We get 1 over 2 e to the negative 2t e to the 2 tau evaluated at a and b. So let's clean some of this up. I'll leave this here. So let's get rid of this. So y of t is going to be equal to 0 for t less than 0, and it's equal to 1 over 2 e to the negative 2t, e to the 2t. Let's finish this real quick down here. So we got this as the result of our integration. And we said, well, the two things we need to integrate over, the two bounds, we need to do from 0 to t and 0 to 2. So for 0 to 2t, we get 1 over 2 e to the negative 2t e to the 2 tau 0 to t, and that's going to be equal to 1 over 2 e to the negative 2t e to the 2t minus 1. Because if we swap out this tau with a t right here, then it just becomes 2t. And if we swap out this tau with a 0 right here, well, 2 times 0 is 0, so we get e to the 0, which is equal to 1. And then we get our result is going to be 1 over 2. We can multiply this in right here, and what we get is e to the power negative 2t plus 2t, which is equal to e to the 0. So that becomes 1 minus e to the negative 2t when we multiply this over to here, right? So we get 1 over 2, 1 minus e to the negative 2t, and that's for 0 is less than t, which is less than 2. And now for our second area, or for our second set of bounds, it's the same result, but we're going from 0 to 2. And we get 1 over 2 e to the negative 2t e to the 4th minus 1. And that's simplified. I mean, you can simplify it more. Right? Well, I guess it wouldn't be even simplifying it. It would be 1 over 2, e to the 4 minus 2t minus e to the negative 2t, which I think it might be uglier. So let's just keep this one right here. I'll put that right there, and then this is for t greater than or equal to 2. And if we look at a plot of this, so here's a plot of this. And from 0 to 2t, we have this. I can't draw this. In this first section here, we have our exponential growth in red, coming up, coming up, coming up, right? And then it turns off. And then we have our exponential decay. And that would make sense if we thought about an RC circuit, just to try to get a little bit of put a little application behind the mumbo jumbo. If we have an RC circuit, so we have some power supply, some DC power supply right there, and then we have this capacitor coming in here, and we have our resistor. So this is C, this is a VDC, and this is an R coming to ground, and we take our output voltage right there. Well, if the capacitor is initially uncharged, and then at t equals 0, we close that switch, well, the voltage is going to build up across the capacitor. We get a voltage there, so that'd be a negative voltage there. So let's concentrate on the voltage across the capacitor. Or I guess we could just swap the circuit around. Let me do that real quick. If we put that there, resistor here, and then our capacitor right here, this is R, here's C, and we take our output voltage right here, VO of T. When we close the switch at T equals 0, if this capacitor is initially uncharged, it's going to be at 0, it's going to be 0, right? And then we close the switch, and then that capacitor is going to charge up exponentially, right? And it's going to stay there. It's going to stay there until if we open this switch back up, I guess this is a poor circuit. Let me give me 1 second here. So here's our capacitor. Here's C, and this is going to ground. And here's our resistor R. And we could have a ground right here. Here's our switch coming in, and that comes down, and then here's our power supply. And if at T equals 0, so we know our capacitor is initially at 0 volts because it's at ground right now. And we can just call this V naught right there. Here's V naught. If we switch this over to the power at T equals 0, we're going to get an exponential rise of the output voltage. And it's going to stay there until we turn this switch back to ground. So if at T equals 2, switch goes back to ground. We're going to discharge our voltage through the resistor and back into ground, and that's going to be an exponential decay. If you've taken circuits 1, then this should all be just recap. And that's essentially what we see here in this plot. And yeah, so there's a little bit of application to why we're studying convolution. Thank you.